Okay, so now I'm going to talk about the Turing machine. And just like the video with the halting problem, I'm not expecting you to understand the Turing machine on a deep level. I just want you to follow, to some extent, what I'm saying because it'll be important for understanding other things. But I'm not going to make you you know, do a Turing machine kind of problem on a homework or a te or the test. Okay. So with that being said, right, in order to talk about Turing machines, I first need to talk about functions and algorithms. So we do functions all the time, right, in algebra. So f of x, right? You plug in x to the function and you get an output. You plug in numbers into the input of these functions and you get an output, and a given function will always generate a unique output for a given input. So examples of this are squaring, right? So x squared equals y. Uh, In this case, x is the input, x squared is the function, and then y is the output. You could also do addition, x plus z equals y. X and z would be the inputs, x plus z is the function, and y is the output. And then with multiplication, right, x times z equals y. X and z are the inputs, x times z is the function, and y is the output. So that's what a function is, okay? And so to talk about algorithms, I need to explain what an algorithm is. And an algorithm for effectively calculating a number theoretic function is a procedure that can be specified in a finite number of steps. It can be unambiguously followed by a human or a mechanical computer, and it will always yield an output for any input for which the function is defined. In the book, the author, Bermudez, is his last name, describes an algorithm as a recipe, except that the only caveat or qualification is that a recipe for a dish you can fail at. You can fail at implementing the recipe. But the important thing about an algorithm is that as long as you follow the steps perfectly, you can't mess it up. You'll get to the right answer. It can be blindly followed and it will always lead to the right solution. So importantly, an algorithm is a number of steps that one is guaranteed to get the correct answer if followed correctly, or it will prove that no solution exists. Uh, and so to talk now about the Turing machine, we'll talk about that now. The Turing machine is an idealized computing machine that can be specified in a purely mathematical way. And so it does not have to take any physical form, right? And as we saw in the video, there's a machine table of a Turing machine, and that's the program. And it specifies the appropriate output for a given input. And the machine table is like the algorithmic instructions, the instructions for how to get from the input to the output. And this was essentially a machine that would mechanize reasoning in a way that did not require any insight, ingenuity, or intuition, right? Because it could be the steps of the algorithm could be followed blindly. This was important because these concepts of insight, for example, were difficult to operationalize or define in a formal way. Um, yeah, so this abstract machine can be realized in many ways, but it's essentially an abstract version of a computer. And a Turing machine would be a machine that can compute a specific function. Okay, so now we'll talk more specifically about the machine. So the idea is, so this is a picture of a sort of Turing machine. It's not really a Turing machine. It's a physical instantiation of a Turing machine. Uh, because, a Turing machine has an infinitely long tape to it, and this has a finite tape. So, but it's supposed to symbolize or represent a Turing machine to some extent. And the machine itself has an infinitely long tape divided into individual cells, and it has a finite alphabet of symbols, of which there must be exactly one symbol in each cell of the tape. And then there's a printer or scanner that can, in a sense, essentially read what is in a given cell, and they can also write over that cell or write in that cell. Yeah, so the machine table of a Turing machine specifies the instructions for the scanner and printer. So when the scanner and printer is in a given state, it can move one cell to the left or to the right. It can erase what's in the cell. It can write a new symbol in that cell, or it can enter into a new state. So the instructions specify what action to carry out given A, the internal state of the machine, and B, the input. So we have these symbols right here, right? So Q of I is the current state of the machine. S of J is the symbol in the square being examined. A is the action that the machine is to perform. And then Q of T is the final internal state of the machine when given an input. When given an input. And so, again, they talk about this in the book, but I'm going to show you this picture here. So the thing above right here, this is the tape, the infinitely long tape. And this is the machine head. It's like the scanner and printer. And it also shows that this machine, right, is in a certain state. Okay, this is the current state of the machine. So I'm going to do an example of this. Um, so hopefully it's relatively fluent. I'm going to try my best. Okay, so here we go. We have these are the rules, which I'm going to elaborate on. Oh, sorry, you can't see. Yeah, these are the rules, which I'm going to elaborate on in a second. And these are the states that you start in, and then this is the state that you might end in, that you go to, right? And so, and this is the action, and this is right here. This is the input. So let's do it. Okay, so um, the other thing I wanted to point out is that this is like the infinitely long tape. Okay. So in this example, we have our current awareness, as the video stated, is that we're in is one. The input is one. So we're in Q1 state, right? We're in the Q1 state, and the symbol that's being examined is one. And so if you're in that state, the action is to replace it with zero and then stay in the Q1 state. So that's what we do, right? We replace it with zero and we stay in the Q1 state. And now in the Q1 state, we're in the Q1 state and the input is zero, right? So what do we do when the input is zero? Well, we move to the right and then we go to the Q2 state, right? So that's what we do. We move to the right. Now we're here and we go to the Q2 state. So these are the two Q2, these are the two Q2 states. So when we're in the Q2 state and the input is one, which is exactly what is symbolized by this row. So when the input is one, the action is to go right and then stay in the Q2 state. So we go right, and then we stay in the Q2 state. And then now, so that means that now we're here, we've gone to the right, and now our input is zero. So we're in the Q2 state, and then the input is zero. And so in this state, we have to, the action is to replace this zero with one, and then go to Q3 state. And that's exactly what we would do. We replaced the zero with one, and now we're in the Q3 state. Okay, now that's probably makes very little sense, and so just know that I'm not going to make you do anything like this on the test or on the homework, but just to give you a flavor of what the Turing machine does and how it works. That's how it works. And so this is, yeah. So what I wanted to say, the brilliance of the Turing machine is that you can create a Turing machine that can calculate every calculable number theoretic function. And the universal Turing machine is a machine that can mimic any individual Turing machine. So individual Turing machines can do one type of function, but a universal Turing machine can mimic any individual Turing machine. And the Turing machine can be characterized in a purely mathematical fashion, and therefore any Turing machine can be inputs to the universal Turing machine. And basically, modern digital computers are essentially universal Turing machines with finite tapes. Of course, it's a bit more complicated than that, I'm sure, but that's essentially the bare bones of what they are. And so the the cool thing he showed is that a universal Turing machine can calculate and figure out the answer to any possible problem that is computable with a simple algorithm, and that all that needs to happen is for that algorithm, the steps of that algorithm to be followed. And the important thing is that these steps can be followed in a blind and mechanical fashion. Uh, right. And so by doing this, you've basically created a way to mechanize at least some parts of thinking or some subset of thinking. All right. So you might be saying, why does this matter, right? Why are we talking about this? Okay. So the universal Turing machine is a model of how information processing can take place. It's a purely algorithmic process. And even though cells on the tape uh, can carry information, can be transferred in a purely mathematical way. Sorry, it's a purely algorithmic process, and the cells on the tape can carry information that can be manipulated and transferred in a purely mechanical way. And so it's basically, intelligent symbol manipulation without needing things like a homunculus, which is, remember what we talked about before in the previous video. So essentially, the stored program with the instructions does the job of what a homunculus does without really needing a homunculus, right? And so therefore, you don't need the infinite regress of homunculi. And more importantly, I think this set the foundation for thinking about the mind as a computer. Sorry. Yeah, so this set the foundation for thinking about the mind as a computer, right? Or the mind is like a universal Turing machine in a sense. So sorry, that was way longer than I had hoped for. In the next video, we're going to talk about formal systems.